We're going to start off this next section with a review of some identities. Now, the reason why we're focusing on these identities is because this chapter is very algebra heavy, and so we're going to be needing to use these a lot throughout the entire chapter. So what are the identities? Well, the first group of identities are the Pythagorean identities. So you might remember sine squared theta plus cosine squared theta equals 1. This was sort of the primary version, and then we've got the tangent squared plus 1 equals secant squared, and 1 plus cotangent squared equals cosecant squared. We got those by taking this and dividing it by either sine squared theta or cosine squared theta. This formula right here actually comes out of drawing a circle and using the formula for sine and cosine. Sine is y over r and cosine is x over r. And if you make the substitution, you get an equation for a circle of radius r. All those things should be in the background when you see this. Now, when it comes to actually using it this chapter, we're not going to use the picture so much, but the picture is the foundation for how all this comes about. Next, we have the negative angle identities. So the negative angle identities, we've written all 6 out here, but they actually just stem from the first two, the sine theta and the cosine theta version. So sine theta is an odd function, which means that sine of negative theta is negative sine theta, and the cosine function is even. Cosine of negative theta equals cosine of theta. The rest of these can be derived from those by just writing down the relationships between these functions and the sine and cosine functions. And last, we have the reciprocal identities. We haven't actually labeled this as a group of identities before, but we've seen them enough. Basically, what they say is that each function has a reciprocal version of it. So sine is the reciprocal of cosecant, cosine is the reciprocal of secant, and tangent is the reciprocal of cotangent. And you can get these, again, by just taking the basic formulas for sine, writing these in terms of sine and cosine, and just writing it out and seeing what you get. And you can verify all of these identities. So these are the identities you're expected to know and be comfortable with as we go forward in this section. We're going to be solving a lot of trigonometric equations, and some of them will get a little complicated. So here are some tricks to help you move forward when you start to get stuck. First of all, never divide by functions. Always use the zero product property. What do we mean by this? Well, suppose you have the equation sine of theta times cosine of theta equals sine of theta. Some students will see this and divide by sine of theta and cancel that out. If you do that, you run the risk of dividing by 0 because you don't know what value theta is. Maybe the sine of theta is equal to 0, and then you divide by 0, and then you've messed everything up. So instead, what you want to do is you always want to try to move towards factoring. Sine theta times cosine theta minus sine theta equals 0. And then use the zero product property from here. Because now when you do the factorization, you will have the explicit case, sine of theta might be equal to 0, which doesn't happen if you go from here and try to divide. Here's the next tip. Minimize the number of functions through substitution. You might have a situation that looks like this. Cosine squared theta plus sine theta is equal to 0. Now, what you're going to do is, if you see this, you have sines and cosines. You can't really do a factorization because you don't have the same terms here. And so what you can do is you can use the trigonometric identities. In particular, you want to be using the Pythagorean identity here, which is if you have, let me screw this up here, sine squared theta plus cosine squared theta equals 1. Right? You can actually use this to write cosine squared theta in terms of sine squared theta. So if you subtract sine squared theta from both sides, you get cosine squared theta is 1 minus sine squared theta. I'm sorry for squeezing it in there. But then that becomes a substitution to here. And now you have just one trigonometric function, and now the factorization will work. And the last one is to look for differences of squares. We're going to run into things like this, 1 minus sine squared theta a lot. And it's important to recognize that this is a difference of squares. This is 1 squared minus sine squared, which can be written as 1 plus sine theta times 1 minus sine of theta. And this will come in handy many times when you have fractions and things like that where you're looking for something to reduce. look for this type of pattern. It'll come up more often than you think. And so here's some quick tips, and we'll go to an example. Here's an example. Solve 2 sine squared t minus cosine t equals 1 on the interval from 0 to 2 pi. So we can see we have a mixture of sine squared and a cosine, and using a Pythagorean identity, we can replace the sine squared with a cosine squared. That will get everything down to a single variable. So I'll go ahead and write out that work again. Sine squared t plus cosine squared t equals 1. And we're trying to solve for sine squared because that's the thing we want to replace. So sine squared t is equal to 1 minus cosine squared t. Now when we make this substitution, we're substituting for the sine squared. So 2 times whatever sine squared is, which is 1 minus cosine squared t, minus cosine of t is equal to 1. So now we have everything down in terms of a single variable. But we need to move towards trying to look at some sort of factoring technique. And so we need to get the right-hand side equal to 0 so that we can use the zero product property. We'll first distribute 2 minus 2 cosine squared t minus cosine of t equals 1. Typically we want the cosine squared term to be positive, the squared term to be positive, so we can either multiply by -1 or just move everything to the right-hand side, which is what I'm going to do here. So 0 is 2 cosine squared t, we're adding, plus cosine t, and then we have this 1, but then we're going to subtract 2, so -1. And now we have to factor. Factoring requires us to use potentially either the quadratic formula or the AC method of factoring, whatever method of factoring you're comfortable with. I actually prefer the AC method because it handles situations that you have non-monic polynomials, meaning that the square term has a coefficient other than 1. And so that works for here. So what does the AC method say? So we're trying to find, you can think of this as 2 times x squared plus x minus 1, if that helps you see this a little bit more clearly. Sometimes students get confused because there's so many terms here. This is just cosine squared, and that's just cosine. So you can think of it that way. So anyway, the AC method. Whoops. The AC method. What does the AC method say? We're looking for pairs of numbers that multiply to the product AC and add to the value B. So what does that look like for here? 2 numbers that multiply to, well, 2 times -1, -2, and add to +1. And now we just have to check, what numbers can we think of that multiply to -2 and add to 1, if any? What pair of numbers works? And so we can see that +2 and -1 is such a combination. 2 times -1 is -2, and 2 plus -1 is +1. And so this helps us to factor. I'm going to bring this down. So 0 equals 2 cosine squared t. This middle term right here is going to be broken up with coefficients, with these coefficients. So we will have +2 of this and -1 of that. So +2 cosine t minus cosine t minus 1. Now this feels a little bit like magic, but basically what we've done here is we've just taken this middle term and we've rewritten it. If we were to combine these together again, 2 cosine minus 1 cosine is 1 cosine, and that's up there. And the point of doing this is it allows us to factor by grouping. So here there's a 2 cosine of t that can come out, and we're left with a cosine of t plus a 1. Over here that's negative and that's negative, so minus cosine of t plus 1, right? So the minus distributes to make that there. And here's where you know if you've done your factoring by grouping correctly. You should have a term in parentheses that is identical. So we have 2 cosine of t minus 1, so that's that minus 1 from that minus sign, and both of these are being multiplied by cosine of t plus 1. And here's where we can use the zero product property. We've now got this times this is equal to 0, so one of these two things must be 0. We're out of space here, so I'm going to erase the board and give myself more space and pick up from there. Okay, so here we are with 0 equals 2 cosine t minus 1 times cosine t plus 1. And by using the zero product property, we're going to set each of these equal to 0. So 2 cosine of t minus 1 is equal to 0. Or we could have cosine of t plus 1 equals 0. So we'll just focus on this side for a moment. What's going to happen? Well, we're going to isolate the cosine of t term. So cosine of t, add 1, divide by 2 is 1/2. and we have to solve this equation. And this pulls back to what we were doing in an earlier section. Let's take a look at the unit circle picture. The cosine function corresponds to the x-coordinate, and we want the x-coordinate to be positive 1/2. So we're looking at a situation where we have solutions in quadrant 1 and quadrant 4. What is the reference angle going to be? Cosine of which angle from 0 to 90, or from 0 to pi over 2, gives us 1/2. And so with a little bit of thinking, and you should be able to find that the reference angle is going to be pi over 3. And so we use that information to help get our t values. Now in this case, because we're only interested on the intervals from 0 to 2 pi, we're not going to worry about the coterminal angles. So this first one is going to be pi over 3. What are we going to get for the second one? Well, for the second one, to get in the fourth quadrant, we have to go all the way around and then subtract off the reference angle. So 2 pi minus pi over 3, which happens to be 5 pi over 3. So these are two solutions so far. And then we have to jump over here and look at the rest of this. So cosine t is equal to 1, or sorry, cosine t is equal to negative 1. What's this going to look like? Once again, focus on the unit circle picture. The cosine is the x-coordinate, and we want the x-coordinate to be negative 1. But since this is a circle of radius 1, we know that's going to be that point. So in fact, there's only going to be one solution from this part. T is equal to pi, and that comes from just looking at the picture. And so in all, we have three possibilities for t. T is pi over 3, pi, or 5 pi over 3. And again, we don't have to worry about coterminal angles because we're asked to solve this on a specific interval. So here's another example. Solve 3 tangent t is equal to sine of t. Now if you look at this, a Pythagorean identity is not going to help us here because it relates sine to cosine and tangent to secant, and those two things aren't interacting. So that's not the right substitution here. And so you have to kind of just work through what other possible substitutions you can make. When in doubt, you can always try to get everything in terms of sines and cosines. It's not always the best move, but it's just something that you need to have in your arsenal of tricks. So 3 sine of t over cosine of t equals sine of t. Well, we had a fraction, so we might as well clear the denominator, multiply both sides by cosine of t. And here's a place where, again, students can run into problems. Don't divide by functions. You might be dividing by 0. Instead, move towards factoring and using the zero product property. So let's move everything over to the left-hand side. 3 sine t minus sine of t cosine of t is equal to 0. There's a sine term in each of these, so we'll factor that out. Sine of t times 3 minus cosine t is equal to 0. Right? So now we have a product of two things, sine of t and 3 minus cosine t equals 0. We use the zero product property. Either sine of t equals 0 or 3 minus cosine t equals 0. Well, this one's already in a form where we can look at the unit circle. Sine of t, sine is the y-coordinate. We want the y-coordinate to be equal to 0. And so that's going to give us those two intersection points, which happen to be at 0 and at pi. In this case, there's no restriction on the domain, so we're just going to get all of them. So t is equal to 0 or pi. And then we have to remember plus 2 pi k, the coterminal angles. Add multiples of, integer multiples of 2 pi. Where k is an integer. Now the book will sometimes simplify this just so that you're aware, because if you actually take a look at these values, I'm going to squeeze that in right up here. 0, 2 pi, 4 pi, 6 pi. That's from this top one. From the lower one, you get pi, 3 pi, 5 pi, and 7 pi. And so with this, you can see that we're actually getting all the integer multiples of pi. So the book will sometimes condense this into a single answer that will look like 0 plus pi k. I find that a little confusing, so I tend to leave it in this form just to remind you that this is coming from two separate solutions. But just be aware that that might happen sometimes in the solutions. Over here, let's solve for cosine of t. Cosine of t, we're going to add it to both sides, is equal to 3. Now this is a different situation. Cosine of t equals 3. Cosine is still the x-coordinate, but we want the x-coordinate to be 3. But if this is a unit circle, equals to 3 is way out here somewhere. What does that mean? That means that there are no solutions. No values of t will get you a point that is the intersection between this line and that circle. So there are no solutions from this part, which means that all your solutions are down here. And this is another example of using factoring to solve. Here is a very complicated looking example. Solve the equation 4 over secant squared theta plus 3 cosine theta is equal to 2 tangent theta cotangent theta on the interval from 0 to 2 pi. Now it's very easy to be overwhelmed at first, but it's also important to be able to take a step back and start thinking about what you can do to simplify this. The first thing to recognize is that 1 over secant squared theta is one of the reciprocal identities. This is actually just cosine squared theta. So 4 cosine squared theta plus 3 cosine theta is equal to. Before we talk about the right-hand side, notice that this left-hand side has simplified significantly already by just recognizing that one substitution. You may not see it all at once, but as long as you're making forward progress, that's a good sign. What can we do with this? 2 tangent theta times cotangent theta. Well, once again, we can draw on the reciprocal identities because cotangent theta is just 1 over tangent theta. And so that substitution allows us to cancel out the tangent thetas. And so we have 4 cosine squared theta plus 3 cosine theta is equal to 2. Now at this point, we see that we have a squared term, cosine squared, so we're going to use the quadratic formula or factor, and so we need to subtract 2 from both sides to get this equal to 0. Okay, so we should check, does it factor? AC method. So AC, remember, it multiplies to AC and add to B. So A times C, 4 times negative 2 is negative 8. So two numbers that multiply to negative 8 and add to 3. And so if you play around with this for a little bit, you're going to quickly discover that it just doesn't work, that there are no integers that accomplish this. And so that tells us we can't factor. When we can't factor, the other technique we have is we have the quadratic formula. Now, this is obviously less preferred because it's a lot messier, but sometimes you got to do what you got to do. So, in this case, our variable is going to be cosine of theta. I'm going to write out the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac, all of this over 2a. Make sure your fraction bar is long enough to capture both parts of the numerator. So when we make the substitution, our b value is 3, so negative 3 plus or minus the square root of 3 squared, which is 9, minus 4 times a times c. So 4 times 4 is 16, times negative 2 is negative 32, so it'll be plus 32, right, minus a negative, all over 2 times a, which is 8. So our cosine of theta is equal to negative 3 plus or minus the square root of 41 over 8. Now at this point it becomes clear that we're going to need to use a calculator. We're going to need to get a decimal approximation to these values, and we can go forward from there, and I'm going to need more space on my board. So right now we have cosine of theta is equal to negative 3 plus or minus the square root of 41 over 8. And so we have to deal with the plus case and the minus case separately. Let's go ahead and start with the plus case. Cosine of theta is equal to negative 3 plus the square root of 41 over 8. And so this is going to have to go into a calculator because we really don't have much else we can do with it. And so when we plug it into a calculator, you get cosine of theta is equal to 0.425. Now, obviously, this is not one of the known values, and so we're going to have to use a calculator, and we're going to have to think about the unit circle picture. Cosine of theta, cosine is the horizontal direction. The horizontal direction is a positive number. So that tells us we're going to have solutions in quadrant 1 and quadrant 4. And when you put this into a calculator, you're going to get the value of the inverse cosine of 0.425 is 1.131. Now remember, this is in radians, and 1.131 radians, this is less than pi over 2 radians, and so this will give us our first quadrant value. How do we get the quadrant how do you get the value in the fourth quadrant? Well, we have to go all the way around and subtract off that angle. So 2 pi minus 1.131, which turns out to be 5.152. We're only interested in the solutions on the interval from 0 to 2 pi, and so we don't have to worry about doing the plus 2 pi k for these. So that takes care of the plus case. What about the minus case? Cosine of theta is equal to negative 3 minus the square root of 41 over 8. When you plug that into a calculator, you get this is negative 1.175. And we draw the unit circle picture. The cosine value is, again, x-coordinate, but the x-coordinate is negative 1.175, which is going to be just outside of the circle. And so this part has no solutions. And so here's an example of solving one of these problems where we ended up using the quadratic formula. The overall process and approach is still the same. But in this case, when we ended up with something that we just couldn't factor, you have no choice. You have to go to the quadratic formula. It gets messy, but sometimes that's what happens. In this section, we're going to look at the sum and difference formulas for the sine and cosine functions. Here are those formulas, and these are formulas that you should memorize. But fortunately, there are some patterns here that will help you keep things straight. First of all, notice that the sum and difference formulas for the sine functions are very similar. In fact, the only difference are the signs here and the signs there. And the same is true of the cosine. For the cosine, the only difference are the signs here and the signs here. For the sine functions, it's plus and plus, minus and minus. For the cosine functions, they're flipped. Now, these are actually just two formulas written out in separate ways. So you actually only need to remember this one and this one, because you can derive the other formulas by using the negative angle formulas. So I'll show you how this works. So let's look at sine of alpha minus beta. We could rewrite subtraction as addition of the opposite, sine of alpha plus negative beta. Now this is a sum of angles, and so we could use the top line. So sine of alpha, cosine of negative beta plus cosine of alpha sine of negative beta. Right, so all we did is instead of writing beta, we have plus negative beta, so we put the negative beta in those positions. From here, we use the negative angle identities. Remember, cosine is an even function, so cosine of negative beta is just cosine of beta. So this is sine alpha cosine beta. And here, the sine function is an odd function, so sine of negative beta is negative sine beta. We can pull that as negative sine out front. And that gives us exactly what we have up here. So really, these formulas are just two formulas. Now, there are derivations of these formulas, and you can go look them up online if you want to. We're not going to be so focused on it. They're just geometry problems, basically, and you should be able to follow them. But for this class, we're just going to focus on applications more so than derivations. Here are a couple examples. Determine the value of sine of pi over 8 cosine of 5 pi over 24 plus cosine of pi over 8 sine of 5 pi over 24. Now, immediately, what comes to mind is grab a calculator and plug it in. And that's not the goal of these problems. The goal of these problems is to help you practice recognizing these formulas. Now, I've written down the sine and cosine formulas down here for just the sums. And of course, for the differences, you just flip the signs of everything. And so our challenge here is to figure out which one of these matches up with the problem. And so if you take a look at it, we have a sine and cosine being mixed together plus cosine and sine. That's going to be this one. And so I'm going to write down that formula underneath it. Sine of alpha cosine of beta plus cosine of alpha sine of beta. And the idea is that by staring at these formulas, you can recognize what alpha is and what beta is, and then apply this formula. So in this case, if we do the comparison, we can see the alpha terms are pi over 8, and the beta terms are 5 pi over 24. So I'll write that over here. Alpha is equal to pi over 8, beta is equal to 5 pi over 24. Now this is nothing more than pattern recognition. Once you know what patterns you're looking at and trying to match up with, it's just a matter of finding the right match. Once we have this, we know that this is equal to sine of alpha plus beta. But since we know alpha and we know beta, we know that this is equal to sine of pi over 8 plus 5 pi over 24. And now we just do the fraction arithmetic. Common denominator of 24, so 3 pi over 24, 3 plus 5 is 8, so this is equal to sine of 8 pi over 24, which is the same as sine of pi over 3. And if you remember your values from the unit circle diagram, we know that this is actually equal to the square root of 3 over 2. And this is a little bit surprising that this whole mess comes down to something that we're actually familiar with, but that's just because of how these formulas work out. By simplifying, by making the substitution and recognizing the patterns, we can actually determine what that value is representing. The second problem is similar, except this time we're asked to find the value of cosine of 15 degrees. Notice we're working in degrees at this point, and we're not given exactly how to do this. Now again, you might just grab a calculator and plug it in and give me a decimal approximation, but this says determine the exact value of it, so that's not going to work. What can we do? Well, we need to figure out how to make 15 degrees a sum or difference of angles that we know. Right, so we have the 30-degree angle, we've got 45 degrees, we've got 60 degrees, we've got 90 degrees. We also have 0 degrees up here. And we need to find some sort of combination that works. And there are multiple choices here. And it doesn't matter which one you use, because as long as you do the calculation correctly, it will all come out the same. So you might do 45 minus 30, you might do 60 minus 45. No other combinations in this list of numbers will work, but that's okay. Let's do this as cosine of 15 degrees is equal to cosine of 45 degrees minus 30 degrees. Right. Cosine of a sum of angles formula, we actually have the difference here, so we're just going to swap the signs. So this is going to be cosine of 45 degrees times cosine of 30 degrees. Instead of a minus, we turn that into a plus, plus sine of 45 degrees sine of 30 degrees. Go back to our unit circle diagram. What are the values here? Cosine of 45 degrees is root 2 over 2. Cosine of 30 degrees. Cosine is the x-coordinate. It's a 30-degree angle, which is a smaller one, so it's going to be the bigger value. Root 3 over 2. Plus sine of 45 is root 2 over 2. Sine of 30 degrees is going to be 1/2. And so when we plug it all in, root 2 times root 3 is root 6. So we have root 6 over 4 plus root 2 over 4, which we can put under a single fraction, root 6 plus root 2 over 4. There are other manipulations you can do to try to simplify that further, but it doesn't actually take you anywhere. So that's how we determine the exact value of cosine 15 degrees. It's interesting because up to this point, we have not had exact expressions for angles other than the 30, 60, 90, and the unit circle diagram values. But what this is showing us is that we have some tools now that allow us to get a few more values out of a few more exact values for the sine and cosine functions. Here's an example of solving an equation using the sum and difference formulas. Solve sine of x cosine of 2x minus cosine x sine of 2x equals negative root 3 over 2. Now once again, this is part of pattern recognition. when you see this combination, something should be going off in your head that this pattern looks familiar. Sine, cosine, minus cosine, sine. And so you have to either remember the formulas, or I've got them written down here, which formulas, or which formula does it match with, and then what are the values of alpha and beta. So I'm going to write underneath it, we have a combination of sine and cosine, so we'll do sine alpha, cosine beta. Now you'll notice that here we have a minus sign up here and plus sign down here, so we know we're going to have to flip the sign when we actually make the substitution. Cosine alpha, sine of beta. Right, so we can see that alpha is x and beta is 2x. And that this whole thing is actually going to be equal to sine of alpha minus beta, right? Again, minus sign here because the sign's flipped relative to that formula. Okay, so we now know what this is, and we know that alpha is x and beta is 2x. So this whole thing becomes sine of x minus 2x is equal to negative square root of 3 over 2. Well, x minus 2x, that's sine of negative x. And now here we have to think some more. Sine of negative x, the negative angle identity. What does that tell us about this expression? Well, sine is an odd function, so the negative sign factors out. Negative sine of x equals negative root 3 over 2. So sine of x is square root of 3 over 2. And now we're getting somewhere. Now we've got this down to a very simple trigonometric equation. We know how to solve this. Let's take a look at our unit circle picture, right? So sine. Sine is the y-coordinate, and we want the y-coordinate to be positive. That's going to give us solutions in quadrants 1 and quadrants 2. The reference angle, sine of what is equal to root 3 over 2? You'll remember that's going to be pi over 3, as that tells us the other angle is pi over 3, or the other reference angle is pi over 3. So x is equal to, we've got pi over 3. The other angle, we have to go full pi to get to here and then pull back by pi over 3. That's going to be 2 pi over 3. And in this case, you see that there's no restriction on the solutions, and so we have to remember the plus 2 pi k. And that gives us the solutions to this equation. Right? So again, the starting point was just recognizing this form, recognizing this pattern. And with more practice and more experience, it'll become easier and easier to recognize these things. Here's an example of proving an identity using the sum and difference formulas. Now here is an identity, and you might recall that when we prove identities, you start from one side and you work your way to the other. Now whether you work left to right or right to left will depend on the problem. And typically we try to look for the side that is more complicated and move towards simpler. In this case, they're roughly equally complicated. This is a mixture of tangents being added and subtracted. Here you have these new formulas to work with. So it doesn't really matter sometimes if you're in this case, and you just try one and get started. I will say that if you start from this side, you can start by substituting in the formulas, and it's going to be more sort of thinking about the algebra. If you start from this side, you're going to do some algebra first, and then you're going to have to rely on pattern recognition to see that you've actually got these formulas in play. And so, again, it's up to you. I'm going to start from the left and work my way to the right. So, sine of a plus b over sine of a minus b. Okay, well, let's make our substitution. Sine of a plus b is going to be sine of a cosine of b plus cosine of a sine of b. And in the denominator, it'll be the same thing, except for we'll have the sign flipped. And so we'll have sine of a cosine of b minus cosine a sine b. Now remember that when you're working with fractions, you cannot break this up into a bunch of different parts. So some students will start canceling things out here and it just becomes a mess. Remember that you can't cancel out unless you have a product of terms on the top and on the bottom, and those terms that you're canceling out are identical. Okay, so what's going to happen here? Well, in this case, we have to take a look at where our goal is. Our goal is to get tangents over here. And if you take a look at what we've got, we don't have anything that looks like tangents. In order for us to have tangents, we need cosines in the denominator. So one way we can handle that is that we can multiply top and bottom of the fraction by the same thing to create those fractions. So sine A cosine B minus, plus cosine A sine B. And then on the bottom, sine A cosine B minus cosine A sine B. And we're going to multiply top and bottom by something, some sort of fraction. And since we want tangent A and tangent B, and that has a cosine A and cosine B in the denominator, right, sine over cosine, we're going to just try that and see what happens. So cosine A cosine B gets really squished over here on the side. That happens sometimes. So we multiplied the top and the bottom by 1 over cosine A cosine B. Now, really important here, we're going to have to use the distributive property, multiplying this by the entire numerator here. So what do we get? Well, if we look at this first term, well, actually, I'm just going to write it out. Sine A cos B over cos A cos B, and similarly for the rest. Cos A sine B over cos A cos B, in the denominator, sine of A cosine of B, or cosine A cosine B, minus cosine A sine B over cosine A cosine B. Having written this all out, we now just look for cancellation. Here, we have a cosine B canceling out. Here, we have a cosine A canceling out. And then same thing here. Cosine B's cancel out, cosine A's cancel out. And what are we left with? Well, here, we have sine over cosine, sine of A over cosine of A, which is tangent A, plus sine B over cosine B, tangent B, all divided by sine A over cosine A is going to be tangent A. Denominator has a minus sign, tangent B, and that's exactly what we were going for. So this is a trick for these types of proofs. In this case, remember, we had to think about where we are going to. We wanted to get tangent terms, and so we needed to get cosines to appear in the denominator somehow without changing the value of the expression. And so that's what this step right here, multiplying by something over itself. We're going to look at a specific application of the sum of angles formulas. And specifically, what we're looking at is we're looking at combining two sinusoidals, so sine bx, cosine bx. And the important thing here is that the period of both of these is the same thing. It turns out that when you have a sum of sines and cosines like that, you can actually write it as a single sine term. And so we're going to, these are the formulas that you need to use, but we're going to show you the logic behind these formulas. And then we'll do an example. Okay, so here are the formulas, and so where does this all come from? What we're going to do is we're actually going to look at the right-hand side of this thing. A sine of bx plus c. And you'll notice that in this case, this bx plus c, the x term is not isolated. It's not like the other one was like b times t minus c or something like that. In this case, it's in this particular form, so do pay attention to that detail. And so what we have here is we can just use the sum of angles formulas. A times the quantity. So this is a sum of angles in the sine function. So sine of bx cosine of c plus cosine of bx sine of c. And now we're going to distribute the a. And we're also going to put the sine bx term on the end. So a cosine of c sine bx plus a sine of c cosine bx. Now the reason I've done this is because if we compare this equation to this equation right here, we'll notice a pattern. M is going to be this part, it's the coefficient of the sine bx, and n is going to be that part, the coefficient of the cosine bx. And you can see right here, if m is equal to a cosine c, and n is a sine c, that by dividing both sides by a, m over a is cosine c, and n over a is sine c, that's a derivation of these two values. M over a is cosine c, that's this one. N over a is sine of c, that's that one. But that still leaves us with the question, what about a squared equals m squared plus n squared? Where does that thing come from? Well, it's actually just a rearrangement of these two expressions. And the trick here is to use the Pythagorean identity. Sine squared plus cosine squared equals 1. So I'll slide in over here. Sine squared c plus cosine squared c equals 1. Right? Well, sine squared is going to be n over a, so n over a squared plus m over a squared equals 1. N squared over a squared plus m squared over a squared is 1. If you multiply both sides by a squared, n squared plus m squared equals a squared. Right? So all of these formulas, they simply come out of plugging stuff in and moving things around until you get the parts to match up. And then also in this last part, just recognizing the Pythagorean identity again. Write 4 root 3 sine of 2x minus 4 cosine 2x as a single sinusoidal function. And here are those formulas. So the first thing we need to do is match everything up. We have m is equal to 4 root 3. We have n is equal to negative 4. So the first thing we want to do is we want to calculate a. So a is going to be equal to the square root of 4 root 3 squared plus negative 4 squared. And we just need to work that out. 4 root 3 squared, so the 4 squared is 16. The root 3 squared is 3, so 16 times 3 is 48. Square root of 48 plus negative 4 squared is 16. 48 and 16 is 64. The square root of 64 is 8. So that takes care of the first part. For the next part, we need to figure out this value of c. What value of c are we going to get? Well, we have cosine of c is equal to m over a, so 4 root 3 over 8, which is the same as root 3 over 2. And then sine of c is going to be n, which is negative 4 over 8, which is negative 1/2. We need to figure out what angle c satisfies those properties. First thing to look at are the quadrants. In this case, we have the cosine term is positive and the sine term is negative. The cosine term corresponds to the x-coordinate, so the x-coordinate is positive. The sine term corresponds to the y-coordinate. The y-coordinate is negative, which means you're down here in quadrant 4. And so this is going to help us because we can get the reference angle, but then this knowing what quadrant it is tells us what the actual value is. So now let's think. Cosine of a reference angle is root 3 over 2. Sine is going to be 1/2. I'm actually going to draw a little triangle since we're looking at both of them. So the root 3 over 2 side is horizontal. The 1/2 side is vertical. Now remember, the angle is technically in the fourth quadrant, so it's flipped over, but I'm just drawing it this way because this is conventional. The question is, what is that reference angle? Well, that reference angle is going to be 30 degrees. The 30-degree angle here, because it's a smaller value, and the 30 degrees is also pi over 6 radians. So that tells us our reference angle. Since we're in the fourth quadrant, we have to go all the way around and then come back by that reference angle. And so 2 pi minus pi over 6 is 11 pi over 6, and this is going to be our value of c. And so when we put it all together, this expression right here, which I'm going to rewrite, 4 root 3 sine of 2x minus 4 cosine of 2x is equal to a, which is 8, times sine of bx, the b is the same throughout, 2x, plus c, plus 11 pi over 6. And if you were to take the sum of angles formula and apply it to this and expand it all out, you should get this. In addition to the sum and difference formulas, we actually have another set of formulas. Now I will say that these formulas are not worth memorizing. If you happen to be in some application where you're using these a lot, you'll probably memorize them through experience. But right now, the actual focus of this is really more algebra practice than it is, here's a bunch of formulas that you just need to cram into your brain. So let's take a look at these. We have the product to sum formulas, which take a product of two sinusoidals and turns them into a sum of sinusoidals. And then we have the sum to product formulas, which take sums and turn them into products. Now specifically, notice that the sum to product formula only has the sum and difference of sines and the sum and difference of cosines, but not a mixture of the two. It turns out if you mix sines and cosines of different periods, you have a big mess on your hands. If you mix sines and cosines of the same period, then you could use the methods that were introduced earlier to simplify that. So here are all the formulas. We could actually derive these formulas using just the sum and difference formulas from earlier. In fact, if you plug them in straight into here, you will see that they are going to be, the algebra just ends up canceling out nicely. Down here it's a bit more complicated, but the same basic principle holds. If you turn this into u over 2 plus v over 2, and that into u over 2 minus v over 2, and then make your substitutions with the sum and difference formulas, this will all work itself out for you. Here's an example. Determine the value of sine of 15 degrees plus sine of 75 degrees. I've already written out the corresponding formula. Sine of u plus sine of v. Sine of 15 degrees plus sine of 75 degrees. So our u is equal to 15 degrees, and our v is equal to 75 degrees. Once you identify the formula, everything else is about the algebra practice. You're going to plug things in, you're going to do some manipulations, and you're going to try not to make mistakes. So here we go. Sine of 15 degrees plus sine of 75 degrees equals 2 times sine of u plus v, so 15 degrees plus 75 degrees over 2, times cosine of u minus v, so 15 minus 75, 15 degrees minus 75 degrees, all over 2. Equals, well, the 2 comes along. 15 plus 75 is 90. 90 over 2 is 45, so sine of 45 degrees times cosine of, let's see, 15 minus 75 is negative 60. Negative 60 divided by 2 is negative 30 degrees. All right, well, now we think. Sine of 45 degrees, well, that one's not too bad. That's root 2 over 2. That's a memorized value. Times cosine of negative 30 degrees. A couple different approaches. We can use the negative angle identity to write this as just cosine of 30 degrees. Alternatively, we can think about the unit circle. Negative 30 degrees, let me just draw that here. Negative 30 degrees is going to be in the fourth quadrant. Right? And then you can use our reference angles and take the value of cosine of 30 degrees. The cosine, in this case, since we're looking at the x-coordinate, it'll stay positive. No matter how you slice it, cosine of negative 30 degrees is root 3 over 2. And now when we simplify, let's see, 2 of those cancel out. You have 2 in the denominator, root 6 over 2. So again, nothing fancy going on here. We just need to identify which formula and make sure we have the right substitutions, and then execute properly from there. In this section, we're going to look at the double angle identities. Here they are. Sine of 2 theta is 2 sine theta cosine theta, and cosine of 2 theta actually has 3 forms: cosine squared theta minus sine squared theta, 2 cosine squared theta minus 1, and 1 minus 2 sine squared theta. Now, initially, this feels like a whole bunch of new equations to memorize, but in fact, this is old information repackaged in a new way. What do I mean by that? Let's look at sine of 2 theta, and we're going to do some manipulations. 2 theta. Well, 2 theta is just theta of theta, so this is sine of theta plus theta. And now we can use the sum of angles formula and apply it to this to see where it takes us. So sine of alpha plus beta is going to be sine of alpha, in this case that's just theta, times cosine of beta, plus cosine alpha sine beta. And again, in this case, alpha and beta are both theta, so theta is everywhere. Well, sine theta, cosine theta, sine theta, the commutative property lets you swap the order, and you see that these are like terms, so we have 2 sine theta, cosine theta. So technically, instead of just memorizing this as a separate formula, you could actually just rederive this every single time. Now, on the other hand, this formula is used often enough that having it memorized separately is also very useful in and of itself. So you have to take make your decision about how you want to do it there. What about the cosine 2 theta? Well, same thing. Cosine of 2 theta is cosine of theta plus theta. And you might remember that the sum of angles for cosine is cosine cosine, so cosine theta times cosine theta minus sine theta sine theta. And you'll see that this is exactly the first equation up here, cosine squared theta minus sine squared theta. Okay, well then, where do these other two formulas come from? Now, if you have enough experience from this, you start to recognize, hey, wait, I see cosine squareds and sine squareds, which means that we might be able to make a substitution using the Pythagorean identity. So again, sine squared theta plus cosine squared theta equals 1. And so sine squared theta is 1 minus cosine squared. So if you plug in 1 minus cosine squared, you'll get that. If you solve for the cosine squared instead, and you get 1 minus sine squared, and you plug that in, and you'll get this other one. So you can see that this is just old information repackaged in a brand new way. And again, it's useful to memorize this not because it's better, but because it's useful. You can always rederive these things from scratch if you had the other formulas memorized, but this is another way that we look at it, and it's useful enough to keep it as a separate topic. Here are a couple applications of the double angle formulas. Determine the value of 2 cosine squared pi over 12 minus 1. So what we have to do with this one is, just like previously, we have to match this up with one of these formulas to figure out which one it's referring to. And so with a little bit of inspection, you'll see 2 cosine squared theta minus 1. So this is going to be 2 cosine squared theta minus 1. And that quantity is cosine of 2 theta. Now at this point, we have to identify the value of theta. We can see right here that theta is equal to pi over 12. And now when we plug this in, we get that this quantity, I'm going to write it in the right order, cosine squared pi over 12 minus 1 is equal to cosine of 2 times theta, 2 pi over 12, which is cosine of pi over 6. And then we think back to the unit circle diagram or the chart. Cosine of pi over 6 is the square root of 3 over 2. Right, so once again, just matching the formula with the one down here, figure out the correct substitutions. Let's look at the next one. Simplify 4 cosine 3x sine of 3x. Well, we come down here and we look at our formula, 2 sine theta cosine theta, and you can see that there are a couple things. I mean, first of all, you can see that they're swapped in order, but that's not the big deal. However, 4 is not 2. And so we can't immediately just dump this into this equation because this part doesn't match up. So the question is, what can we do about this? And here's where you're going to have to rely on your algebraic experience in order to push yourself forward. When we think about 4 cosine of 3x times sine of 3x, we might recognize that 4 is just 2 times 2. So I can write this as 2 times 2 sine 3x cosine 3x. And here I've also swapped the order to make it match more closely with our formula. And now you can see that this part right here is the exact thing that we're looking for. And so this is 2 times, and you come down here, that's sine of 2 theta, sine of 2 times the theta value, and the theta value is 3x. And so this is equal to 2 times sine of 6x. One of the problems that we've run into in the past was the calculation of one trigonometric function based on values about another trigonometric function. This is the same thing except using the double angle formulas. If sine of theta is equal to 3/5 and theta is in the second quadrant, determine the value of sine of 2 theta and cosine of 2 theta. Now it turns out for the cosine of 2 theta, we can calculate this right away. And the reason why is because there's a representation of this that only refers to sine of theta. And so this is 1 minus 2 sine squared theta. And so in this case, we're going to have 1 minus 2 times 3/5 quantity squared. And we just have to do the fraction arithmetic correctly. 3/5 squared is 9/25. 2 times 9/25, you might remember that if you have an integer, you could always put it over 1. So 18/25, 1 minus 18/25, which is equal to 7/25. And that's one of our two values. Now to get the value of sine of 2 theta, we actually need to know what the value of cosine theta is, because the formula of sine of 2 theta is 2 sine theta cosine theta. And that cosine theta value is one that we currently don't have. So let's take a look. Sine of theta is 3/5 and theta is in the second quadrant. So our theta looks like that. And we know that sine of theta is equal to 3/5. Now, just as before, we can use either an algebraic technique or a geometric technique here. So for the geometric technique, we want to think of this as y over r. For the algebraic technique, we use cosine squared theta plus sine squared theta equals 1. The Pythagorean identity, make a substitution, and go from there. In this case, I'm going to go ahead and use the geometric approach. So we have a right triangle, and here's our reference angle, which refers to, this triangle here. So we have y is equal to 3 and r is equal to 5. So y, the height, is 3, and the hypotenuse is 5. You can see that this is going to be a 3, 4, 5 right triangle, but because we're going to the left side in the second quadrant, that 4 is negative. So we have cosine of theta is equal to negative 4/5. Now that we have this value, it's just a matter of plugging things in. This is equal to 2 times 3/5 times negative 4/5. 2, I'll go ahead and put it over 1. 2 over 1 times 3 over 5 times negative 4 over 5. So it's going to be positive, positive, negative. So it's going to be a negative. The numerator, 2 times 3 is 6. 6 times 4 is 24. Denominator is 5 times 5, which is 25. So sine of 2 theta is negative 24/25. And then cosine of 2 theta is 7/25. Now, just like before, you will notice that we did not calculate what the angle theta really is. We only know these two values about it. We don't actually know the angle. And so that's one of the tricky parts about this, is that your job is not actually to find theta, but to use the formulas to calculate these particular values. And now we'll do an example of proving an identity using the double angle formulas. Prove that secant of 2 alpha is equal to secant squared alpha over 2 minus secant squared alpha. Now if you notice, this is actually a double angle formula for the secant function. All the functions have double angle formulas, and they're just going to be applications of these down here. So let's see how this one works. We are proving an identity, so we need to start from one side and work our way to the other. And typically we start from the more complicated side and work our way towards a simpler. In this case, the right-hand side is the complicated side. It's a fraction with secants in the numerator and the denominator. So let's start there. Secant squared alpha over 2 minus secant squared alpha. Now the first thing to observe is that all these functions down here involve sines and cosines. And so writing this as secant is not going to help us move forward. So we need to rewrite all of this as cosines. So 1 over cosine squared alpha, 2 minus 1 over cosine squared alpha. Okay, well now we've got the problem of fractions inside of fractions. Now we could try to multiply by the reciprocal of the denominator. That would require us to find like terms down here first, which we could do. But if we notice these fractions, the denominators of each of those fractions is exactly the same. And so in this case it makes more sense to clear those fractions by multiplying the top and the bottom by cosine squared alpha. And this will eliminate the fraction inside a fraction problem as well. So let's see what we have. If we multiply by cosine squared alpha, that cancels out that. So we have just a 1 in the numerator. Over, well, we distribute 2 cosine squared alpha minus 1. And the cancellation happens just like it did in the numerator. And now things are starting to look familiar. 2 cosine squared alpha minus 1. 2 cosine squared theta minus 1. So this is 1 over cosine of 2 alpha. And once we recognize this as a secant function, we are done. We've made it to the other side of the equation. So once again, it's a matter of just plugging stuff in, making substitutions, and following your nose on the algebra. There's no rule that tells you exactly what the next step is going to be. You just kind of have to look and see what you have and use that knowledge and your experience to go from there. One of the applications of the double angle formulas is the derivation of the power reduction identities. So what are the power reduction identities? Cosine squared alpha is equal to 1 plus cosine 2 alpha over 2, and sine squared alpha is 1 minus cosine 2 alpha over 2. Now, why are they called the power reduction identities? Well, you see you have a cosine squared here, and it turns into a cosine to the first. There's kind of this conservation of complexity. Cosine squared is more complicated than cosine to the first, but it's not just a regular cosine because we have to change the angle on the inside here. Now, why might we want to do that? It turns out that for some mathematical purposes, a cosine squared is more complicated to work with than a cosine to the first, even if you have to change the angle here. And so this turns out to be one of the reasons why we like these formulas. We can reduce the power of the cosine to make it so that we have maybe a more complicated angle, but we don't have powers of the cosine terms. So where does this come from? Well, the big hint is the cosine 2 alpha term. Cosine of 2 alpha. We have our formulas. So we have one of them that says that this is 2 cosine squared alpha minus 1. And the other one says that this is 1 minus 2 sine squared alpha. And your intuition is probably starting to kick in. All we need to do is take these equations and solve for either cosine squared or sine squared. Let's focus on this left-hand side first. We need to isolate the cosine squared terms. We're going to add 1 to both sides. So 1 plus cosine of 2 alpha is equal to 2 cosine squared alpha. And then divide both sides by 2. 1 plus cosine 2 alpha all over 2 is equal to cosine squared alpha. And pretty much the exact same thing happens on the other side. So if this is set equal to cosine 2 alpha, and we try to isolate the sine squared, we're going to subtract 1 from both sides. So negative 2 sine squared alpha is equal to negative 1 plus cosine 2 alpha. We're going to divide by negative 2 to get sine squared alpha is equal to, let's see, we'll distribute the negative sign, so it turns into 1 minus cosine 2 alpha all over 2. And so this is the derivation of the power reduction identities. So here's an application of the power reduction formulas. Write cosine squared theta, sine squared theta in terms of cosine functions to the first power. So let's take a look at this. Now the first thing is clearly that we're going to use the power reduction formulas. So we have one for cosine squared and one for sine squared. So we can plug that in right away. 1 plus cosine 2 theta all over 2 times 1 minus cosine 2 theta all over 2. Now you might look at this and say, okay, well, cosines are all to the first power, so we're done, except that we have a product here that we need to multiply out, and you'll see what happens. So in the denominator, 2 times 2 is 4. In the numerator, we have 1 plus something times 1 minus something. That leads to a difference of squareds. So 1 minus cosine squared 2 theta. And now here we can see that there is in fact another power of cosine that's not 1, and so we have to simplify this further. What is that going to look like? Well, what we're going to have to do is we're going to have to make this substitution again. pay close attention to what's inside the cosine squared function. Cosine squared alpha, cosine squared 2 theta. So when we end up here, cosine of 2 alpha, that's going to be cosine of 2 times 2 theta, or cosine of 4 theta. So we need to be very careful with that because that's something that's very easy to mess up if you're going quickly. So here we go. 1 plus cosine of 4 theta all over 2. Okay, once again, fractions inside of fractions, we have a bunch of simplification to do. What can we do here? Well, again, you can multiply by the reciprocal of the denominator. In this case, we only have one fraction term right here, and so I think it's simpler to multiply top and bottom by 2, and that will clear out the fraction inside of fraction piece. When you do this, you do need to be careful. You do need to make sure you distribute. So, denominator first, because that part's pretty easy. What happens if we distribute? 2 times 1 is 2. Minus. Now the 2's cancel out, so we have minus parentheses 1 plus cosine of 4 theta. A little bit of simplification here. 2 minus, well, the minus sign distributes, so 2 minus 1 is 1. And then the minus sign distributes minus cosine of 4 theta all over 8. And so this is an application of the power reduction formulas. The half-angle identities is just another set of identities that we can derive using the techniques from this section. In fact, it's probably easiest to derive these from the power reduction identities. Let's start with cosine squared theta is equal to 1 plus cosine 2 theta over 2. Now we're just going to make a couple substitutions. We're going to replace theta with theta over 2. So then we get cosine squared of theta over 2 is equal to 1 plus cosine of, well, 2 theta becomes 2 times theta over 2, and the 2's cancel out, so cosine theta over 2. And now we see that we just take the square root of both sides. Remember, when we take the square root, we have to include a plus or minus. The derivation of the sine one is very similar. Now, when using this, we have one new idea that we have to work with. We have a plus or minus. This corresponds to the same concept from before, where we had to look at the quadrant where the angle is lying in, but in this case we have to be a little bit more careful because which angle does this refer to? The plus or minus actually refers to this angle here, the theta over 2. And so when you do these problems, you have to remember that you have to pick the plus or the minus based on the theta over 2 angle and not the theta angle. The easiest way to keep this in mind is just to remember, like, we are calculating cosine of theta over 2. This is the thing we want in the end. And so whatever the sign is has to match up with this piece right here. Here's an example. Find an exact value of cosine of 75 degrees. So we have to calculate cosine of 75 degrees. This is not one of our known values from the unit circle table, but we're going to use instead this half angle formula. Now when we look at this, we have to determine what the value of theta will result in cosine of 75 degrees. We are not setting theta to be 75 degrees. And so one of the things you really need to be careful of here is to make sure that you are writing something that matches the formula that we have. Theta over 2. So 75 degrees is 150 degrees over 2. So in this case, the theta is actually 150 degrees. And this throws a lot of students off that are in the mindset of just plugging stuff into formulas without thinking. So take a moment and really think about this to make sure you understand why the theta is 150 degrees and not 75 degrees. Once we get that, we have plus or minus the square root of 1 plus cosine of 150 degrees all over 2. We'll go ahead and calculate the part under the square root first and then figure out the plus or minus later. So 150 degrees. Well, 150 degrees is going to be in the second quadrant, and the reference angle is going to be 30 degrees. Since it's cosine, in the second quadrant, it's going to be negative. So this is going to be plus or minus the square root of 1 minus, now the reference angle is 30 degrees, cosine of 30 degrees is the square root of 3 over 2, all of that over 2. So we can go ahead and simplify this, plus or minus the square root of, let's see, we have a 2 in the denominator there, and that's the only thing in the denominator, so, or the denominator in the numerator, and so we can multiply top and bottom by 2. 2 minus square root of 3 over 4. And now we have to make that decision about the plus or minus. Which angle are we thinking about for this plus or minus? Is it the 150 degrees or is it the 75 degrees? Now remember, we are calculating this quantity right here, and this quantity is either going to be positive or negative depending on whether the 75 degree angle is in the first or second or third or fourth quadrant. So in this case, 75 degrees is in the first quadrant, cosine is positive in first quadrant, so we will take the plus case here, square root of 2 minus root 3 over 4. There's one more simplification we can do right here, which is square root of 2 minus root 3 all over 2, because the square root of 4 is 2. Either one of these answers for me would be acceptable. Using the half angle formula to calculate cosine of 75 degrees opens up a really interesting feature. Here's one way of calculating cosine 75 degrees using the half angle formulas. And here's calculating cosine of 75 degrees using the sum of angles formula. And if you look at the final results, it is not immediately clear that these are actually the same thing, but they are. And you can prove this to yourself by squaring both of these and then simplifying and comparing your results. And so there's a very interesting feature here that we have very different expressions that have the exact same quantity. Now this isn't a course where we can go much deeper into why this happens or how we can create representations like this. But it's interesting to see that it's right in front of us that these two things look entirely different, and it's not obvious that they're the same thing. But because we know they're both equal to cosine 75 degrees, they really are the same thing. In this chapter, we've been looking at situations where we have a constant midline and a constant amplitude. And that has led us to graphs that look basically like this. Here's our midline. And then we have our amplitude, which gives us an upper limit and a lower limit. And then our function oscillates in between those two, right? Our sinusoidal function oscillates between those two values. Well, this is one way of setting things up. But in fact, it's possible to do many other things with this general framework. Instead of our midline being constant, it could be a function. Instead of the amplitude being a constant, it can also be a function. And so this gives us a bunch of different shapes that we can look at. So here's an example. If we were to have, instead of a horizontal midline, if the midline were an increasing function, and we still have our sine and a constant amplitude, well, the constant amplitude will put us above by a fixed amount and below by a fixed amount. And now the graph will look something more like this. Now you want to be careful that you're not just taking the graph and rotating it, because it still needs to satisfy the vertical line test. But you have this type of shape. Alternatively, you can have a variable amplitude. So, for example, let's say we have a fixed midline. But now instead of a constant amplitude, let's say we have an increasing amplitude. And now our function will take on a shape that looks more like this. And so both of these shapes are easily accessible from the setup that we currently have. Let's take a look at that. So right now we're looking at equations where of the form y equals a times sine, or possibly a cosine, b times x minus c plus d. This a part is the amplitude. And previously, it had been a constant. But to get something like this, all we need to do is replace that constant with some other function. And that will create this, which is sometimes called the envelope, this envelope of these vibrations. Similarly over here, this right here is going to be our midline. And so if the midline is some other function, so in this case, a line with increasing slope, but it could also be a parabola, it could be whatever we want it to be, we will still have the same underlying structure of thinking about the midline and then think about variations from the midline. But that midline will now be a variable function, variable changing with different input values, and not just a straight horizontal line here. We can also mix the two of these together. We can actually have a function with both a variable midline and a variable amplitude. So this is just to give you a bit of an overview of what else can happen with these things. The best way for us to get a handle on the idea of variable amplitude and variable midline is to think through a couple examples. So here's one. The number of tourists visiting a resort averages 4,000 people annually and oscillates seasonally 1,000 above and below the average. The number of tourists increased by 200 per year. Create a model for the number of tourists starting from the peak season after T years. So we're going to do this, not this problem first, but we're just going to think a little bit about what's happening. So here is a graph of the number of tourists that are in this area, in this resort. Now, if we ignore the part about increasing by 200 per year and just sort of think about the behavior that we have, here's our average at 4,000, and it's going to go from above 5,000 to below 3,000. And it's going to have this oscillating behavior. It's going to go down in the next peak season, and then the quiet season, and then peak season, and so on. And so every year, we have this 1 year cycle, and then another year, we have another cycle. All right, so this is the picture without the increasing tourism. What does it mean then if we say we have increasing tourism? We're going to have a similar picture, except now, instead of having a flat average, that average is going to be increasing. We're still going to have this behavior of starting above, ending up below, and then above again after 1 year. But now there's another motion to take into consideration, which is that we've got this increasing midline. And so our problem is to create a model that takes into account all of this information. So let's take a look at this. I'm going to make an equation down here. Y equals, I'm going to write out the generic one first. A times either a sine or a cosine, we've got to figure out, times some quantity in terms of t plus d. In this case, I'm going to set the midline to 0 just to make life easy on us. And that's where also we have to figure out which function we're talking about. So we're talking about starting from the peak season, which is starting from above here. And that's going to be a cosine function. And so once we set that the beginning is here, then our horizontal shift c is equal to 0, and we can start from this point. And so we just have to get these values. The amplitude in this problem, the amount that we're going above and below the average, even in this situation, is going to be 1,000. So this is going to be 1,000 cosine of bt plus d. Okay, well, what is b? Well, remember that b is the value that corresponds to the period. The period is going to be 1 year, and b is 2 pi over the period, so b is 2 pi over 1, so 2 pi t. And so now the tricky part is this, the d. 4,000 people annually at the beginning and increases by 200 per year. So increasing by 200 per year. So at year 1, this midline right here is going to be 4,200 whereas it started off here at 4,000, right? So how do we get an equation of a line that increases by 200 per year? Well, you can think of this as as slope-intercept form. We have the intercept, we know the slope is 200 per year. So this will be 4,000 plus the slope is increased by 200 per year, 200t. I'm going to put parentheses around this, although it's not strictly necessary. And the reason why is to emphasize that this right here represents the midline. And if you're not sure, you can always check this by thinking about a couple values. After 1 year, there should be 4,200, and you plug in t is equal to 1, you get that. After 2 years, it increases by another 200, so that's 4,400. Set t equal to 2, and you get 4,400. And so this right here is the model. Now you'll notice that a lot of this relies on your ability to create the basic models with constant amplitude and constant midline. But now that we're sort of stretching these things, most of this stays intact, and we just have this additional feature where we're saying, okay, well, what if the midline is changing? What changes? Well, the part that changes is just the midline portion. Here is another example. A population of fish oscillates 50 above and below the average during the year. The average starts at 800 fish and increases by 3% each month. Model the population in terms of months since January, assuming that the population is at its lowest in that month. Okay, so once again, we're going to try to break this apart. Now, there is something different in this one compared to the previous one, which is that our rate of increase is actually going to be a percentage rather than a fixed quantity. And so we're going to have to think about that part. But to begin with, what we want to do is we want to think about what's happening without the change of midline. This will help wrap our mind around what's going on. So we're starting at the low. So we have some midline here. In this case, it's starting at 800. It starts at its low, which is 50 below, which was 750. And it's going to go above and below. And this cycle repeats after 1 year. The peak is going to be 50 above, which is 850. Now, the thing to pay attention to is that the time is measured in months. So I'm not going to put a 1 here for where it repeats. I'm going to put a 12 here because 12 months later is when it repeats. And this is going to impact when we calculate the period, the values that we're going to be using. Right, so here's our function, and we can immediately see this is going to be another negative cosine because it's starting at low, going to high, going to low. And so we could actually start writing some of this in. It's going to be negative 50 cosine of something, something, something plus something, right? So this is our BT term. And so I have to figure out B. Remember, B is 2 pi over the period. So B equals 2 pi over the period. The period is 12 months, so 2 pi over 12, which is pi over 6. So pi over 6t. Right, so this is the part that ignores the changing midline, just sets up our oscillation. And so now let's take a look at the midline. So for the midline, we're increasing by 3% per month. What does that mean? Well, at the beginning, we'll have 800. That's the starting point. And then it'll be 3% more than that. So it's going to be 800 plus 3% of 800. And if you look at that, that ends up being 1.03 times 800. Just write 3% as a decimal, 0.03, and then factor out the 800. This is what you get. Well, what happens another month later? What is that going to look like? Well, the math of this gets a little bit messy. This is actually something that you did back in precalculus with exponential growth. But basically, we're going to have this quantity, 800 plus 3% times 800, plus it's going to grow by 3% of this. So 3% times 800 plus 3% times 800. Now again, it looks a little messy, but you can see they both have this 800 plus 3% times 800 term. So we'll factor that out. And if we factor that out, we'll have a 1 plus 3%, or 1.03. And if you think about this quantity, well, we just calculated it, that's also 1.03. So we have 1.03 times 800 times 1.03, 1.03 squared times 800. And this is starting to show us what the pattern will be. Every month that goes by, you're going to multiply by another 1.03 because that represents the previous population plus 3% more. And so when we put this all together, move that plus sign over here because I didn't leave myself quite enough space. This is going to be 1.03 to the 10th power times 800. And so the general pattern that we see, if it increases by 3% per month, that's 1.03, 1 plus the 3% for every month that happens. It's raised to the teeth power because it's compounding with the previous values. When working with problems that involve a variable amplitude, one particular application comes to mind, which is that of a spring that's vibrating back and forth, but with friction to slow down those vibrations. These situations are known as damped harmonic oscillation, and we're going to take a look at the shape of those things as we work through this problem. A spring with natural length 20 feet is pulled back 6 feet and released. It oscillates once every 2 seconds. Its amplitude decreases by 20% each second. Model the position of the spring t seconds after being released. Now, these problems are set up in a number of different ways. Sometimes you have something hanging from the ceiling, but since this says pulled back, the implication from that, for me at least, says that it's held horizontally. So you've got a spring and it's attached to a thing that you can grab onto. Right. And so the natural length of the spring, well, natural length of the spring is the spring when you're not adding extra force to it. And so that natural length is going to be 20 feet. And then what's going to happen? It's going to be pulled back by 6 feet. So pulled back, think back away from the wall. And so if it's pulled back by 20 feet, or by 6 feet, then the 20 feet becomes 26 feet. And then when you let it go, what's going to happen? Well, since you're pulling back on the spring, when you let it go, the spring is wanting to pull back, so the box, or whatever it is it's attached to, will swing back this way. But because of its momentum, it will typically go past the 20 feet, and get short, and then get long again, and short, and you'll get this vibrating pattern like this. And so we would need to try to create a model for this. So let's take a look. Now, just as we did before, we're going to try to pretend everything is going to pretend that everything has fixed values first, and then consider what's happening with the variable aspect of it. So 20 feet is the natural length. We pull it back 6 feet, so we pull it back to 26 feet. And if we let it go, it'll oscillate back and forth. And the low value is going to be whatever it is, in this case 14. But the thing we want to think about is the period, because that's what this picture is helping us to get. So it oscillates once every 2 seconds. So after 2 seconds, it's repeating itself. This part is giving us information about the b value. B is 2 pi over the period, which in this case is 2 pi over 2, which is just pi. The other thing we get from this graph is that we have a cosine function because we're starting at the top. It's going down back up, so it's a positive cosine function. So the y value is going to be equal to a positive something, because that's the amplitude, which is the variable part, cosine of pi t. And then in this case, the midline is constant, so that part is just going to be plus 20. And really we need to figure out what's happening here with the amplitude. And that part is embedded right here. The amplitude decreases by 20% each section. Now, just like the example with the population growing at a certain percentage rate, we had an exponential function. The same thing's going to happen here. Since it's going to decrease by 20% each section, we're going to subtract 20% each second. So it's going to be 0.8 to the 2th power. Whoops. That's the amount it's going to change by, 0.8 to the 2th power. But then we also have the initial 6 feet. Right, so this value right here, it feels like it comes out of nowhere at first. With a little bit of practice and experience, it feels much more intuitive. Basically, what it's saying is that we're starting off with 6 feet of oscillation. 1 second later, it's going to be 6 minus 20% of 6. 20% times 6. And so then when you factor out the 6 on this, you get 1 minus 20%, or 1 minus 0.2, which is 0.8 times 6. And then the next stage is going to be 20% away from this. So 6 minus 20% times 6 minus 20% of that part. And I'm running out of space here, but this is exactly the same calculation we did with the population model previously. And so you're going to factor out another 0.8, so it's going to be 0.8 to the teeth power times the 6. And so this is what leads us to this value right here for the variable amplitude. And when we go ahead and graph this, I'm going to erase this part right here. When we go ahead and graph this, here's what it'll look like. Here's our midline at 20. It starts off up here at 26, but then the vibrations get smaller and smaller and smaller. And that corresponds to friction slowing things down, and eventually it'll look like it'll settle down. So here's one example of using damped harmonic oscillation, or doing a damped harmonic oscillation model and using a variable amplitude to do it. Here's another problem of the same type. A spring with natural length 30 centimeters is pulled out 10 centimeters and released. It oscillates 4 times each second. After 2 seconds, the amplitude has decreased to 5 centimeters. Model the position of the spring. All right, so once again, we're going to think about everything as if there is no changing amplitude, and that will get us started. So it's going to start off with a natural length of 30, and we're going to pull it out 10 centimeters. So pull it out sounds like it's getting longer. So it's going to be 40. It's going to start up here, go down and up, and down and up, and so on. Now in this case it says it oscillates 4 times each second. So if it oscillates 4 times each second, when does it repeat for the first time? And this is something that students get messed up with all the time because they're not slowing down to think about the words of the word problem. They'll just say, okay, well, the period is 4. That's not what this is saying. 4 times per second, meaning that in 1 second it does this 4 times, which means that it takes a quarter of a second for it to repeat. So the period is a quarter of a second. Very confusing for students if you're trying to go too fast, but if you just slow it down and think and read the words, it's much easier. So our b value, which is 2 pi over the period, is 2 pi over 1/4, which is going to be 8 pi. Right? And again, we can also see here that's going to be a cosine function, positive cosine function, because it's starting at the top, going down and going up again. So y equals something something cosine of 8 pi t, and then our midline is also constant, so we can put that in, plus 30. So then we have to deal with this changing amplitude, the variable amplitude. So the only part of this problem that tells us there's a changing amplitude is that after 2 seconds, the amplitude has decreased to 5 centimeters. So at t equals 0, we have an amplitude of 10, and at t equals 2, the amplitude is 5. And we are trying to come up with some sort of expression that captures this behavior. Now, in general, what our formula will look like, it'll always look like some sort of constant times another constant to some power t, right? So this is usually the initial value, and this is the percent decrease. And our job is to figure out what these things are. Well, the initial value, obviously, that's going to be 10, because then when t equals 0, that's the starting point. So it's going to be 10 times something, something, something to the tth power. Whatever this value is, has to have the property that when t is equal to 2, this is going to be 1/2, because the new amplitude is going to be half of what it was before. So it has the property that x squared, when t is equal to 2, is equal to 1/2. Now this, again, this will take a little bit of practice, and in a class that was more focused on probably more like a physics class where you have to do this a lot, we'd spend a lot more time with this. For now, I just want to sort of keep our eye on the sort of big picture here. We are just going through this process to figure out what the percent decrease is per second. And so this tells us that x is equal to the square root of 1/2, and if you actually work that out, that ends up being about 0.707. And so our y value, again, I left myself not enough room, is going to be the initial t times 0.707 raised to the tth power. Alternatively, you can leave the exact value there, 10 times square root of 1/2 to the tth power, cosine 8 pi t, plus 30. So for these problems and the problems with the variable midline, the ideas here are, again, we're not going super deep into this, we're just sort of showing you the ideas. And most of the setup here is exactly the same setup as we did before. The only thing that we're changing is either going to be the amplitude or the midline. And then that comes from reading the words and just setting up some basic equations. For this class, it's either going to be a linear changing amplitude, or excuse me, a linearly changing midline, an exponential changing midline, or an exponentially changing amplitude.